Question 4. A large tank containing this amount of air, this temperature, is connected to a converting diverging nozzle with a throat area of 2967 millimeters squared, to which the air is exiting. A normal shock sits in the point where it is this much. Okay, the nozzle area, exit area is this much. What are the Mach numbers just before and after the shock? What are the stagnation temperatures and static pressures before and after the shock? The flow from the tank to the point of sheet is isentropic. The flow after the shock is also isentropic. The air in the tank is considered static conditions. So let us draw the problem. So we have a large tank connected to a converging diverging nozzle. Okay, so this is the static state. P naught is equal to 860 kPa, and T naught is equal to 352 K. Okay, the throat is this, and then they say the shock sits at a point where the area is this much. So we had this previous question before, right? In a previous video. Is the shock sitting here or here? Because it could be the case that this area is, 1613, and this area is also 1613. Okay, so the question is, which one? Is it the left side one or the right side one? The answer is the right side one. Why? It's because you have to look at the progression of the flow. See, this started as stagnation condition, right? Stagnation means velocity equals 0, and therefore Mach number equals 0. Since Mach number is 0, which is less than 1, this started out as subsonic. So if it started out subsonic, it must go through the converging section to accelerate. Okay? Only after the throat, at the throat is a critical state, okay, where Mach number equals to 1. And only after the throat in the diverging section, then it will be supersonic. Okay? Only in the diverging section will the Mach number be greater than 1. So in the diverging section, it will undergo supersonic acceleration. Okay? It will undergo supersonic acceleration. My point is that only when the flow is supersonic can a shock occur. Okay, so always remember that the structure of a shock, if the flow is to the right, it must be such that immediately upstream of the shock is supersonic, and immediately downstream of the shock is subsonic. But you see here, in the converging section, there is no supersonic flow, right? All of this is subsonic. Therefore, a shock cannot occur in the converging section of the nozzle. And therefore, we conclude that it must occur in the diverging section where supersonic flow is occurring. Okay? So we label the point upstream and downstream of the shock as point 1 and point 2. Okay, hold on. My OneNote just lagged. Okay, yeah. We label the point upstream and downstream of the shock as 1 and 2. Okay, they told us the exit area is 161. Sorry, not 161. 2258. Then, because 1 and 2 are, because the shock is infinitesimally thin, we can consider the section at 1 and 2 having the same area. In other words, A1 to A2 is to 1613. Okay? Yeah. Okay, so this is the set of things that they want us to find, which is very long. M1, M2, P01, P02, P1, and P2. Okay? Let us find the Mach number at point 1. can we find the Mach number of 0.1? And the answer is yes. Okay. From what I mentioned just now, the throat is at critical condition, right? Because this is where the throat is the point at which the cross-section area has a stationary value. Okay? In other words, dA equals to 0. So therefore, here must be critical. In other words, Mach number equal to 1. Okay, so this is a critical point. So the throat area is the critical area. Okay, so this is A star. Okay, so A star. So therefore, and we also are given the cross-section area at 0.1, right? If we know the critical area and the cross-section area at 0.1, we can find the Mach number using the area ratio formula. The area ratio formula I'm talking about is this one. Okay, so apply this formula to 0.1. Okay, so this one is just AT. Then we just sub this in. Right, actually this is millimeter squared, but they will cancel. Okay, so we don't have to care about the units. Okay, so let's pop this into our calculator. So on the left hand side we have this. On the right hand side, bring the fraction over, so you simply subtract the giant fraction. The Mach number is unknown, so replace it with x. Okay. Okay. So again, we have the situation where we have two roots, but which is the correct root? So you see, one root is less than 1, and one root is more than 1. And the answer is, we take the root that is more than 1. So this one, 1.99. But let me see, is that really 1.99? Yeah, it's actually 1.986. Okay, so let me go back here. Okay, so from our calculator, we have obtained that M1 is equals to 1.986. The reason why it is 1.986, right? Take a look. See, 1 is the point that is immediately upstream of the shock. If it is immediately upstream of the shock, it must be supersonic, and therefore it must be Mach number greater than 1. So we cannot take the root, which is less than 1 as well, okay? Because Mach number 0.1 is supersonic. Okay, so once we know M1, right? Once M1 is known, M2 can be solved using the shock relations. Okay, so if you go back to the shock formulas, we shall use this one because M1 is known, so therefore we can find M2. So you can find M2 to be 0.579759. Okay, so we have found M1, M2. We P not 1, right? It's just the stagnation pressure that they give us. So you see, 0 to 1 is connected by an isentropic process. Therefore, the stagnation pressure of 1 is just this. Okay, so yeah, basically P naught 1 is 860 kPa. Now what about P naught 2? So let me check my working. So P naught 2, right? You can actually use your tables to find it, but let me show you how I did it. It doesn't matter. Okay? You can use the tables or you can use my way. So my way is, first I found P1. Okay. So let's go ahead and find P1. So in order to find P1, right? Since you have the stagnation pressure of 0.1 and you have the Mach number of 0.1, you can use the isentropic flow relations. Okay, you can use the isentropic flow relations. So this is given. P1 is unknown. Then you use the isentropic flow relations. You already found the Mach number just now. Therefore, P1 can be found to be 112.3 kPa. Okay, so we have found one of the things that we are asked to find, namely this. Okay, can we find P2? And the answer is yes, right? Because in 1 and 2 are related by a shock. So therefore, we need to use the shock formulas. And the shock formula we are going to use to find P2 is this one, right? The pressure ratio. Okay, so if we use the pressure ratio, P2 over P1, sub in what you know, P2 is unknown, P1 is known. Oh, sorry, it's not 8, it's 3. 3. So the what do you call this? The Mach number 1 is what you know. Mach number 2 is also what you have found earlier. Seven, 9 squared. Okay, so therefore P2 is your only unknown, and therefore P2 is 498.1 kPa. Finally, we can find the stagnation point of 0.2, right? The stagnation point of 0.2 and 0.2 itself is related by an isentropic process. Okay, so therefore use the isentropic flow relations. Okay, so the isentropic flow relations say that P naught 2 or P2, this is unknown, this is known, which is what we just found. And then we can just use the formula that they provided. Mach number at 0.2 is 0.579. Okay, yeah, so we found everything that they wanted. We also found this, and we also found this. Okay, so this is question 4 completed. Take a look at question 5. Okay, question 5 is related to the next topic, namely Fanno-line flow. Okay, so yeah, I don't see any shocks here. So yeah, it's the next topic, which is Fanno-line flow. But let me do it anyways. Room air is drawn into an insulated duct through a smoothly contoured converging nozzle. Okay, so let us draw out the problem. We have a converging nozzle, and it leads to a constant area duct. Okay, the duct is insulated, so I'm going to denote the insulation using hatch lines. Okay, the room conditions are this. So the room can be assumed to be stagnation conditions. So we will label this as naught, and T naught, change degrees Celsius to Kelvin is 300 Kelvin. P naught is 101.3 kPa. Okay, the duct diameter is this in meters. The pressure at the duct inlet, so the nozzle outlet, meaning say here, is 90 kPa. Find the mass flow rate of the duct. Okay, so they wanted to find m dot, and then after that, the range of back pressures for it to be choked. Let's do this one at a time. So how to find m dot? So m dot is given by rho a v, and it looks like the only relevant point I can use is point 1. Okay, I know the cross-section area of point 1, because I know the diameter of the duct. But what about rho 1? Okay, I need to find rho 1. So I'm gonna use the equation of state to find rho 1. Therefore, I need the pressure and temperature first. I need the pressure and temperature at point 1. Because 0 and 1 are related by an isentropic process, I shall use the isentropic flow relations. So the formulas that I showed you so many times already. Yeah, so I'm not going to show you again. I'm just going to directly use it. So this is 300 T1 plus 2 plus. Okay, it looks like I don't have the Mach number, right? I need to find the Mach number first, so I cannot use this. But what do I know? Well, they give me the stagnation pressure and pressure at point 1, right? In other words, they give me the pressure at point 1 and its corresponding stagnation pressure. So if you know a static condition and its corresponding stagnation condition, you can find the Mach number. Okay, so P naught over P1, you use this formula. Okay, sub in the things that you know first. And then you use the formula that you know, which is the isentropic flow relations. Okay, so you see M1 is your only unknown, therefore you can find M1 is 0.414553. Okay, so once you know the Mach number at point 1, you can find the temperature at point 1. So the temperature, stagnation temperature is known, static temperature is unknown. You use the temperature ratio formula. Oops. Oop. You find that your temperature is 290.0 Kelvin. Okay, so using equation of state, you can find the density. So this is 90,007.0. Your density will be 1.081. Okay, you already know your area. Now you need to find your velocity. Velocity is not given, but velocity can be found using the Mach number given by this formula. Okay, Mach number is what we found just now, 0.415. Then speed of sound is given by KRT1. And so you can just sub everything in. 1.4 times 287 times temperature at point 1 is 290.0. Okay, so you can find your velocity to be 141.5. Okay, so you can find your mass flow rate, which is your mass flow is given by the density multiplied by cross-section area multiplied by the velocity, which is 0.075 kilograms per second. Right? Now, the next question, they say, find the range of back pressures for which the duct is considered choked. Okay, so you should watch my previous videos for this explanation, right? Where I have a pressure line here, then this is the back pressure. So you see, this is the exit pressure, this is the back pressure. You're controlling the back pressure, so this is PB. And then you are measuring the exit pressure. So this is a choking point, choke. So you can, before it is choked, sorry, before the flow starts choking, as you bring down PB, PE will simply follow along PB. However, once you bring the back pressure down below the choking point, your PE, right, will simply remain at the choke pressure. Okay, in other words, the critical pressure. So in order to find the pressure, the range of back pressures for which the flow is choked, right? In other words, okay, from here downwards, this is the range of back pressures for which the duct flow is choked. Okay, you need to find this pressure, and this pressure happens to be the critical pressure. Okay, so we need to find the critical pressure. Okay, so to find the critical pressure, we need to use the this formula. Okay, so what kind of flow is this? This flow, right, where you have no heat transfer. Wait, what did it say? Yeah, no heat transfer because it says it's insulated. So adiabatic. And then there is some friction. So I'm just gonna assume that there's friction. If it is adiabatic with friction, then this is what you call a Fanno-line flow. Okay, so we'll talk more about Fanno-line flow in the next video, but right now I just want to introduce you which relations to use. Okay, so this we had to use the Fanno-line flow relation. So you go back up. The Fanno-line flow relations is this box here. Now, which one do I use? Remember, I want to find the critical pressure, right? So I shall use this one. Okay, and I'm going to apply it to point 1 because I know the Mach number at point 1 and I know the pressure at point 1. Okay, so apply the Fanno-line relations to point 1. You will get P1 over P star. Okay, sub in the known values. So P1 is given. P star is unknown. Your Mach number is found already from the previous question. Then you just apply the formulas as it is. Okay, so P star is your only unknown. Therefore, you found P star to be 34.6. Okay, so let's go back to this diagram here. So the value of the pressure at which choking just occurs is 34.6 kPa. So that means anything below 34.6 kPa will make the flow choked. Okay, so therefore, your final answer should be this. PE is less than 34.6 kPa. Okay, this range of pressure causes the duct flow to choke. Okay, yes. So that's tutorial 3 finished. Okay, so I hope you found this video to be helpful. And if you did, uh, yeah, and if you found this video to be helpful, please consider donating me to PayPal. Okay, so it really helps the channel to grow. Thank you.